Everybody, welcome back to another calculus video. In this video, we are going to be talking about integration by substitution. You might say, well, okay, what's that? Well, so far, we've focused a lot on developing various integral rules corresponding to different rules of differentiation. So some of the derivative rules that we covered were, for instance, constant rule, power rule, scalar multiple rule, the sum rule, derivatives of the natural exponential function and natural log of x, and we developed integral rules corresponding to each one of those. Now, you might ask, what are some of the other differentiation rules? Well, there's the product rule, the quotient rule, and the chain rule. Those are kind of the other three big ones. And, well, okay, is there a way to develop integral rules corresponding to those? The answer is yes to all three. The product rule one is a little more complicated, as is the quotient rule one. In fact, I've only ever seen the product rule one done. I'm sure you can do it for the quotient rule, but I haven't done it. And the product rule one, as I said, is more complicated. So, for now, let's skip to covering the integral corresponding to the chain rule, because that's actually going to be a very helpful and simple to understand integral for us. Alright, so we're going to call this process integration by substitution. And let's start off with an example, and then from the example we'll develop the general theory. Let's say we wanted to evaluate the integral of 3 times 3x plus 4 to the 10th power dx. You might say, okay, well, we do know how to evaluate the integral of polynomials. Right? So I could, if I wanted to, I could expand this all out and multiply it. But practically, something to the 10th power, that's ridiculous to try to expand. So we should probably try to come up with a better way. And what we're going to do is we're going to make a clever substitution. We see that there's a clear inside and outside to this function, with the inside being 3x plus 4. So what if we just said, hey, let u equal 3x plus 4. The common name for this process is a u substitution for this exact reason, although technically you could use whatever letter you wanted for the place u. Okay, well, if we let u equal 3x plus 4, that would handle rewriting this. But what about this 3dx part? Then, using the rules of differentials that we covered back in section 3.7, du is equal to the derivative of this thing, which would be 3 dx, right? You can think of it as du dx would be 3, so du is equal to 3 dx. And now, if we plug both of those substitutions into our integral, we see that the integral of 3 times 3x plus 4 to the 10th dx, let's just group the 3 and the dx real fast, because that's what is grouped right here. That's equal to the integral of 3x plus 4 to the 10th power times 3 dx. Now, by our substitution, that's the integral of u to the 10th power, and then this is du. And we know how to integrate that. That's just the power rule of integration at work. And that would say, oh, it's u to the 11th over 11 plus c. But what is u? U is just 3x plus 4. Boom. So now we have our original integral all in terms of x. And this is going to be the general process we're going to use. Integration by substitution is the art of picking a proper u, or v, or whatever letter you want, and using that to make your integral simpler in terms of your new variables, and then you can convert it back after the fact. So in that way, integrals are kind of like puzzles, because figuring out this proper substitution, sometimes it's obvious, sometimes it requires being a little bit clever, but it's a very powerful technique. So, let's see in general why this thing works. let's say capital F of x is an antiderivative of little f of x. Okay, so what does that mean? That means f prime of x is equal to fx. That's what it means to be an antiderivative. Alright? Well, by the chain rule, or you can also think of it as, in another way, the integral of f of x dx is f of x. Let's see, right? Those are the two ways to think about antiderivatives. What does the chain rule say? If we plug something in to capital F of x, so let's say we had the derivative of f of g of x, the first version of the chain rule says, hey, that's f prime of g of x times g prime of x. Or in other words, since f prime is equal to little f of g of x times g prime of x. So now our rules of integration tell us, right, our general formula for integrals saying, hey, this is an antiderivative of something in this format. So the integral of little f of g of x times g prime of x dx is equal to capital F of g of x plus c. Under the substitution, u is equal to g of x. Well, in this case, differential rules tell us du would be g prime of x dx. If we put that substitution into both sides of this integral, we get that the integral of f of u du would be capital F of u plus c. So that's just the general idea for this process, saying, hey, yes, you can make a valid u substitution, integrate with respect to u, and then plug it all back in later, and that is all perfectly valid to do. Alright, so let's detail that out algorithmically, and then we'll do some examples. So your actual four-step process for this whole thing. Step one is choosing your proper substitution. You have free reign over what you choose to do your substitution with. Now, some substitutions are more useful than others. For instance, this would probably be the least useful substitution. Oh no, I've just changed all the x's to be u's, right? Because in that case, du would be dx. And now you've just changed a letter. Okay, that doesn't help at all. But there are more useful substitutions, and the more you do this, the more intuition you develop for what a useful substitution might be. Secondly, you find, okay, we've made the substitution u is equal to g of x. Now we need to deal with that dx part of the integral. So now you're going to find du, which is equal to g prime of x dx by our rules of differentials. So now you can always solve for dx in terms of du and g prime of x and substitute that in. Sometimes it's easiest to get something like this in the form of the integral, and then you can just plug in a du. Don't worry about that, so this was confusing. It'll make more sense once we do some examples. Next, once you have these things all in there, you substitute u and du in. And the goal is to get it all in terms of u. A proper u substitution will not leave any sort of x or dx behind at the end of it. So that's one way to know you're making proper choices. And step 4, you evaluate the integral in terms of u. So you just do the resulting integral in u that's given to you, and then convert back to x. So to summarize this process, all we're doing is we're saying, hey, choose a useful substitution so you can take your integral that is in x world and move it over into u world, where things are a bit simpler. And now once we're over here, we can actually compute the integral and then shift back over to x world to get things all in the terms that we wanted to start with. So let's do a few examples of this. And this, more than anything else, is something that you just need to practice a lot. The more practice you do, the more facile this will be for you. Alright, so to start us off, let's take two kind of nice ones. Let's evaluate the integral of 3x squared times x cubed minus 7 cubed dx, and the integral of 2x plus 1 times x squared plus x to the 4th power dx. Now, when you're trying to look for this substitution u is equal to g of x, oftentimes the most helpful thing you can do is say, okay, what's the most complicated part of the integral? I'm going to make that my u, because that just puts it all in terms of u, very simple piece, and then hopefully everything shakes out from there. So let's do this first one. The integral of 3x squared times x cubed minus 7 cubed dx. Alright, what substitution should I make? Well, it looks like x cubed minus 7 cubed is probably the most complicated part of my integral. So I'm going to make x cubed minus 7 my u. So I'm just going to put that a little thing over here to the side. Let's let u equal x cubed minus 7. And if this doesn't work out, fine. We can always go back and try another substitution, but this one will work out. Because if we choose du like this, then du is equal to, okay, du will be 3x squared, the derivative of this thing, dx, by our differential rules. And now, oh look, we have a 3x squared dx. So this integral converts directly into terms of u. We have u cubed from here, and then these two parts together combine to give us a du. Oh, that's a nice and easy integral to compute. It's just power. That's u to the 4th over 4 plus c. Plugging back in our substitution for u, that gives us x cubed minus 7 to the 4th power divided by 4 plus c. So, very complicated looking integral, but handled very quickly by this technique. Goes to show just how strong this technique is. Let's try the other one. Let's see. the integral of 2x plus 1 times x squared plus x to the 4th power dx. Okay. Well, let's try to find a u sub. It seems like there's two groupings, and we're trying to figure out which one is more complicated in terms of what should we make our u sub. Well, okay, let's try one u sub, and we'll see why it's not a good choice. Let's say you were like, okay, let's let u equal 2x plus 1. And then du would be 2 dx. Okay, so if we just try to plug this substitution into our integral, what would it become? Well, we have a u, then we have this x squared plus x to the 4th. And I'm not really sure how to get this in terms of our u easily, right? There's no way to nice and simply convert it to be all in terms of u without any x's flying around at all, right? Like, there's just not an easy way to do that. Much less getting this dx by itself. Or, sorry, in terms of du. That actually wouldn't be that bad. But I don't really know how to deal with this part in terms of this u substitution. So maybe that's not a good choice of u sub. Maybe a better choice would be saying, hey, this thing to the 4th power, maybe that's a better thing to get out of the way. And why is that? Well, because the derivative of x squared plus x is going to be 2x plus 1. So that'll make everything work out very nicely. If you let u equal x squared plus x, du is 2x plus 1 dx. And those substitutions take care of everything in the integral quite nicely. That becomes equal to the integral of u to the 4th power du, which is just u to the 5th over 5 plus c by the power. Now, substituting back in our u gives us x squared plus x to the 5th power divided by 5 plus c. Boom. So, a proper u substitution, things tend to fall out, if not nicely, at least a little bit nicer, you know? And if you try to make an improper u substitution, one of the first clues that you've made an improper choice of u sub is if there's a part of your integral that you just can't really easily fit in terms of u. Let's do another example. In fact, I think the rest of this video will just be various examples. So you guys can have all that exposure. Okay. Let's evaluate the integral of 12 times the square root of 12x plus 1 dx. Excuse me. Which I will rewrite as integral of 12 times 12x plus 1 to the 1/2 power dx. It seems like there's a nice and clear choice of u sub here. More complicated part is right there. So let's let u equal 12x plus 1. And note, I'm making it just the inside portion. I'm not making it to the 1/2 power, because then I'd be taking a complicated derivative that doesn't appear in my integral. So we're just going to let u be the inside portion almost all of the time. In this case, du would be, derivative of this is 12 dx. So, under this substitution, this integral is equal to 12 dx is our du, and this is u to the 1/2. Nice. Power rule now says this is equal to u to the 3/2 divided by 3/2 plus c. Dividing by 3/2 is the same as multiplying by 2/3. So it's going to be 2/3, and then substituting back in, times 12x plus 1 the 3/2 plus c. Nice. So, all the examples we've done so far, the substitution has worked, quote-unquote, perfectly. Right? All the pieces of, for instance, du have been inside of our integral. Well, what happens if that's not the case? Well, one, it could be a sign of a bad choice of substitution. But there's one case in particular that we can easily kind of fix. And that's if we're off by just a scalar multiple. Right? So let's say instead of u being, or instead of at 12 here, we had a 6. Right? So then it wouldn't fit perfectly, but we can actually fix situations like that. So let's see that. Let's try evaluating the integral of x times x squared plus 1 to the 7th and the integral of 3x squared times the cube root of 2x cubed minus 7. Okay, let's take the first one first. Makes sense to do that, right? Okay, the integral of x times x squared plus 1 to the 7th dx. Okay, there's a pretty clear, complicated part on the inside. So under the u substitution, u is equal to x squared plus 1, and du is equal to, well, it'd be 2x dx. What happens? I don't have an x. Or sorry, I don't have a 2x. I just have an 2x dx. I just have an x dx. Okay. How can we deal with that? Excuse me. Well, let's solve for dx in terms of du. This thing tells us that du divided by 2x is equal to dx. So let's just plug all of those things in as best as we can. And I'll show you two ways to do this, so if this way doesn't make you feel comfortable, there will be a second way. If we just plug in what we have, this fits. We get u to the 7th. I don't have a natural du by itself, but I do have dx and I can plug in. I still have this x out here, and I have du divided by 2x. X and x cancel, and we're left with 1/2 u to the 7th du. But that works, right? 1/2 can pull out of the integral. Scalar multiples are nice. They play nice with integrals. And now that's something we can do. That'll be 1/2 times u to the 8th divided by 8 plus c. Multiplying everything through substituting back in gives you x squared plus 1 to the 8th divided by 16 plus c. Alright, so that's one way to handle a problem like that. But let's figure out another way. Maybe you're not comfortable doing this whole jazz because you're like, well, you're supposed to not have any x's left over after you substitute. But there's x's. They do cancel out. But I can understand being discomforted by this. I didn't like that way when I first did it. So let's see a way to kind of fiddle around with it in x form first that helps you not have to do crap like this. It's really the same thing, just on the other side. Let's make the same exact u substitution. Right? We still want that x squared plus 1 gone. And I say, okay, well, I don't have a 2x dx, I have an x dx. But 1 is 1, but 1/2 times 2. True fact. And we can exploit this. Here's how we'll exploit it. we'll write this as being the integral of 1/2 times 2x, x squared plus 1 to the 7th, dx. And now under our u substitution, the 1/2 stays, but the 2x dx becomes our du, and this is still just u to the 7th. So we end up with the exact same thing. Right, from here, process is exactly the same, but it's just another way to get there. Sometimes this is more helpful if it's not off by just a scalar. Sometimes you can do weird things and have it all cancel out still. I don't think I'll give anything like that in this class though. So yeah, this is another way to do it if you're not comfortable solving and doing this work with differentials. You can just work with it in terms of scalar multiples. Let's do that other example. And I think I'll stick with the second way for now, just because it tends to be a little faster. Although the first way is more precise. Alright. Well, it looks like this is probably the most complicated part of the integral, something under a cube root. So let's make our u substitution accordingly. Let's make the u sub, u is equal to 2x cubed minus 7. In this case, du is 6x squared dx. Well, I don't have a 6x squared dx. I do have a 3x squared dx. Let's use the exact same trick as we did over here. This is equal to the integral of 1/2. And if you want, you can write this outside of the integral as well. Scalar multiples play nicely with that. It's going to be 1/2 times 6x squared. So x cubed minus 7 to the 1/3 dx. And now we have all the pieces parts of our u substitution already present within our integrand. This would be the integral of 1/2 times u to the 1/3. And then 6x squared dx is our du. Now the scalar multiple rule and power rule tell you that it'll be 1/2 times u to the 1/3 plus 1 is 4/3 divided by 4/3 plus c. Dividing by 4/3 is the same as multiplying by 3/4. So you'll end up with 3/8. Back substituting in for our u is 2x cubed plus 7 to the 4/3 plus c. And that would be our final answer in this case. Alright, so here is a good place to kind of stop and check yourself and say, okay, am I getting what's going on with all this u substitution crap? Do I understand how this scalar multiple thing works if the du substitution is just off by a single scalar? Can I deal with that? Okay, once you're confident with that, let's move on to some more complicated examples using some of our other integral rules. For instance, let's evaluate the integral of e to the 2x dx and the indefinite integral of the square root of x times e to the 4x to the 3/2 power dx. So one of those is a little more complicated than the other. Let's do the first one. Integral of e to the 2x dx. Well, okay, what do we know? We know that integral of e to the u du is equal to e to the u. standard rule for e to the x, just using the u instead. So this suggests that our u should be whatever is in the top of e to the x. So let's do that substitution. Let's let u equal 2x. In that case, du is 2 dx. Well, I don't have a 2 dx, I just have a single dx. Not a problem. This is equal to the integral of 1/2 times 2. I keep using 1/2 and 2, but it works with like 1/3 and 3, or even like 3/4 and 4/3, right? Whatever the clever choice of fractions is, it works. Times 2e to the 2x dx, which is just pulling out that 1/2. That's 1/2 times the integral of e to the u du. That's our u. Those two parts are our du. That's 1/2 e to the u plus c, but e to the u is just e to the 2x. And as always, we can always check our work by taking the derivative of what we get down here and seeing that it matches what we had under the integral sign. If we took the derivative of this, plus c would go away. E to the 2x, that derivative is 2e to the 2x, and the 2 would cancel with that 1/2, so we'd be left with e to the 2x. So we're good. Let's do the other example, the more complicated. Same idea, we're going to let whatever's in the top part of the u be our, in the top part of the e to the be our u sub. That's a pretty common goal, so that's just one of your first places to check if you have e to something, maybe the to the something is a good idea for your u sub. At least a good first shot. And let's rewrite the square root of x as x to the 1/2 power. Just to make our lives a little simpler. Keep track of everything. Under the u substitution, u is equal to 4x to the 3/2. Then du would be what? Well, it's going to be 3/2 times 4, which is 12 divided by 2. aka 6, x to the 1/2 dx. Alright, well, the form matches that form. We're only off by a scalar multiple. We proceed. We say, oh, that will be equal to the integral of 1/6 times 6x to the 1/2 e to the 4x to the 3/2 dx. And now we have all the proper parts of our u sub. That's equal to 1/6, just pulling that 1/6 outside of the integral sign, times the integral of e to the u du. So e to the u, and then those parts make our du up. And that's equal to 1/6 e to the u plus c. So the whole goal for integration by substitution is to get our integral into a simpler form that we already know how to deal with, whether that's a power rule style thing, or whether it's the integral of e to the u kind of a thing, right? Because those are nice forms that work very quickly. Let's do another couple examples, and then we'll call it good. Let me see how many more I set up for us. 1, 2, 3, and then an IVD. Okay, so 3 more examples like this, and then we'll do an initial value problem, and then we'll call it good. Let's evaluate the integrals of 2x over x squared plus 1 dx and the integral of 9x cubed divided by 4x to the 4th minus 7 dx. Alright, so what do we do in this case? Well, the only real integral I know at this point in the course of fraction style is I know for sure that the integral of 1 over x dx is the natural log of the absolute value of x plus c. So maybe if I have a fraction that isn't just numbers, right? Maybe I should be looking to get it into a form that looks like this via u substitution. So let's try it with these ones. The integral of 2x over x squared plus 1 dx. Well, if we let u equal x squared plus 1, our denominator, since that's what we want, right? We want 1 over x in our denominator, or in our case, we want 1 over u du. Maybe I should just let the whole denominator be u. And if we try that, then du would be 2x times dx. And that's exactly what we have inside of our integral. This now becomes the integral of, okay, 2x dx, right? You can think of the dx as being in the top of that fraction, its multiplication. Well, that's du. X squared plus 1 is u. So we have 1 over u du, aka du divided by u. We know that. That is the natural log of the absolute value of u. Plus c. Substituting back in gives you the natural log of the absolute value of x squared plus 1. Plus c. Pro tip, this thing is always positive, so if you wanted, you could just write that as the natural log of x squared plus 1 plus c, since we're working with just real numbers, not complex ones. But for the sake of argument, let's just say that stuff. Let's do the other end. The integral of 9x cubed divided by 4x to the 4th minus 7. Okay, well, figure out proper use of it. Has a fraction. Looks like x to the 4th, the derivative of x to the 4th is x something with x to the 3rd. So it looks like this is kind of the good pattern where we'll have a du over u. Let's work with it. Let's let u equal 4x to the 4th minus 7. Then du would be 16x cubed. So very close to dx. So very close to what we have on top. Let's work with this one then. Then this integral is equal to the integral of 9 divided by 16 times 16 x cubed dx divided by 4x to the 4th minus 7. And that's precisely the form we need in order to integrate it. This will be 9/16 pulling that scalar out times the integral of du divided by u. Sick. That's exactly what we want. This is 9/16 times the natural log of u. That's the value of u. Plus c, which is 9/16 times the natural log of the absolute value of 4x to the fourth minus 7 plus c. Bingo. Let's do one more example, then an initial value problem, and then we'll call it good. So, general, powerful for taking derivatives, even more powerful when trying to evaluate integrals. Let's evaluate the integral of the natural log of x plus 4 all to the third power divided by x plus 4 dx. Man, what the hell are we supposed to do with that? Can't rate this video for kids anymore, I guess. Okay, so what do we do with this? Well, natural logs seem to be the most complicated part of this whole thing. So maybe I can just subsume that whole thing in, right? Because I have a natural log cubed. That seems like a clear outer portion. This seems like a clear inner portion. So let's just try a couple different u subs. We'll try the correct one first, and then we'll try an incorrect one and see where it fails. Correct u sub would be saying u is equal to the natural log of x plus 4. Why? Because then du is equal to, by rules for natural logs, 1 over x plus 4 dx. And this can be viewed as 1 divided by x plus 4 times the natural log cubed dx. So then, under this u sub, this is equal to the integral of 1 over x plus 4, let's say dx over x plus 4, times the natural log of x plus 4, all cubed. Under our u substitution, that is du, and this is u, so we would have integral of u cubed du. And from there, it's just a nice, easy application of the product rule. Yeah, so we'd have the natural log of x plus 4 all to the fourth power divided by 4 plus c. So that's the correct u substitution. Let's see what an incorrect one would have been and why. Let's say you said, okay, a more specific inside would have just been x plus 4. Sure, let's try it. It's not like anything goes wrong if we try a bad u sub. It just will give us some clues that we should try another one. So let's try maybe v equal to x plus 4. In that case, dv would just be dx. If you just tried plugging those straight into the integral, that would say, okay, everywhere I see an x plus 4, I'll put a v, and everywhere I see a dx, I'll put a dv. That'll be equal to the integral of natural log of v cubed divided by v dv. Is that simpler? Yes. Do I know how to integrate it? Still no. But this actually doesn't mean we can just give up on this problem. If you want to, you can do a u sub from here. And say, okay, well, that didn't work. Let's substitute further. I still seem to have this natural log of v cubed. Let's now let u equal the natural log of v. And then du would be 1 over v dv. Now converting this integral from v world to u world would give us the integral of u cubed du. Here's our dv divided by v, 1 over v dv, and here's our u. We know how to do that. So that's u to the fourth over 4 plus c. And now we're trying to get all the way back to x world. But I don't know u in terms of x. I only know u in terms of v. But we can still work with that. If we put u, go back from u world to v world, that would equal natural log of v to the fourth power divided by 4 plus c. So now I have it in terms of v world. And now we can go from v world back to x world. And that'll give us x to the fourth over 4. Or sorry, not x to the fourth, gosh. What am I talking about? Natural log of x plus 4. That's what our v is. To the fourth, all divided by 4 plus c, right? Using that substitution right there. So, when it comes to making choices for u-subs, sometimes things will go really well. And when you try to make the substitution, it won't convert all the way into terms of the new variable. Like that first example that we did where something went wrong. Then, scrap the whole thing. It's no good. Find a new u-sub. But sometimes, it will convert all the way into the terms of the new variable, but it just won't be simple enough for me to integrate yet. Then you can choose to try to go back and find the proper one and do it all in one step. You're welcome to try that. Or you can just keep going and say, well, okay, let's make another substitution here. And look at that. That one worked out to be something that I can do. Did it. And now I just need to make sure that I convert all the way back to x. So I went from x to v to u. I got something in u. Now that means I need to go back to v and then back to x. Right here. But as you can see, we get the same answer whether we do it all in one step or whether we do it in 2 separate ones. So that's the nice thing about integration is as long as you're making substitutions that do transform the entire integral, you've always made progress. Multiple pieces to the puzzle. Let's do one more example of integration, solving a initial value problem, and then I think that'll be it for this video. Let's solve the IVP given by y'all catch that? That's the IVP. Okay, f prime of x is equal to 3 times x squared plus 4 times 1/3 x cubed plus 4x all to the 7th power and f of 0, not f prime of 0, f of 0 is equal to 3. So let's solve this IVP. By our standard procedure for solving initial value problems, f of x will be the integral, f of x plus c will be the integral of f prime of x dx, which in our case is the integral of 3 times x squared plus 4 times 1/3 x cubed plus 4x to the 7th dx. Now let's make a u-sub. If I make the u-sub, I see here that the derivative of an x cubed is an x squared, so maybe I'm going to try to like this term, u. And then my dx, hopefully, or my du will hopefully work out. Let's try. If we make the substitution u is equal to 1/3 x cubed plus 4x, then du will be x squared plus 4 dx. Cool, so it does work exactly like we wanted. Let's just plug those into our integral. We We have an extra 3 times here, but that's okay. That doesn't change our problem at all. That's just going to be 3 times. Okay, we have u to the 7th, and then this chunk and this chunk make a du. Scalar multiple rule says that's 3 times the integral of u to the 7th du. Power rule then says, hey, that's 3 times u to the 8th over 8 plus c. Substituting back in gives us 3/8 times u was 1/3 x cubed plus 4x all to the 8th power plus c. So we've solved the integral. Now, to solve the actual initial value problem, we impose this condition. And again, the difference here is we're saying, okay, here's an entire family of solutions that satisfy this chunk. Now I want to find the specific function that also satisfies this initial condition. To do that, we know that f of 0 is equal to 3. But what is f of 0? Or sorry, let's just say f of x is this thing. Right, you can choose that one to be 0. Anyways, I'm going off my rocker here. It's just f of x. Okay, so what is f of 0? F of 0 is 0 plugged into this thing. Zero, 0, so this whole thing's 0, that's all 0. C. Sweet, so we already get told what C is for free. C is 3. So now our final f of x will be 3/8 times 1/3 x to the 4th plus 4x all to the 8th power plus. And that would be the unique f of x that satisfies our initial value. Alright, I think that's all for this video. Have a great rest of your day.